Hello everyone. So my name is José Pérez, and I'm here presenting the paper I've co-authored entitled Incentive-Based Load Shifting Dynamics and Aggregators Response Predictability. So this paper is a result from a study performed by IST together with MIT. So as a motivation, we know policymakers and the European Commission, namely, have recently established frameworks to reach targets for clean energy transition. In this case, for the EU, it is just by 2030, and also to reach climate neutrality by 2050. So reaching these targets will require novel solutions. We know the current electric grid has a relatively simple architecture, where generation is largely predictable and also deliberately dispatched. However, as penetration of renewable generation increases, together with the also increasing adoption of electric vehicles, we believe this premise is changing at an impressive rate. And so in this figure here, we can see a load commitment timescale. We can see where could demand response be useful depending on the way response is controlled, always as a resource of flexibility. And so we reckon that here in a day ahead load commitment timescale, demand response could assume an important role on what could be called the change of paradigm from generation following the load to loads following generation. So for this matter, we stand on a model first proposed in a former paper from Professor Pedro Carvalho and Luís Ferreira. In this model, and also throughout this study, loads are assumed as being time shiftable, time constrained, and also incompressible. And also, every load use is also considered instantaneous. This looking at this figure on the left means that every load here represented by a step can be shifted ahead until it collides with the next one. So by looking at this figure, we see this first load on timestamp 4, it could be shifted ahead until timestamp 7, which is what is happening in the figures below. So when this load collides with the next one, it's the next load use that is shifted ahead instead. So that's what's happening in this last figure. And this means that in our case, shifting is only constrained by the load use ahead. And so this is our way of representing loads with maximum flexibility. And that's how we can study load shifting, truly intrinsic dynamics. So after modeling the process of load shifting, each individual load shifting process is represented as a particle hopping process in a one-dimensional lattice of cells, so a string of cells, each cell representing a time period here. In the lattice, cells are either occupied by exactly one load particle or are empty. And shifting takes place by hopping between cells in one direction only, time direction, in this case from left to right. And so because particles can only be shifted ahead on 20 cells, this process of consecutive shifting can be seen as a traveling process with elastic collisions with particles ahead. So this process is therefore dynamic. Both the number of particles available to be moved ahead and their flexibility depends always on the number of particles one has decided to move ahead in a previous time period. So for example, in this figure on top, on the first row, we are showing the original schedule on this figure on the left, which is the same as the previous slide. And then here below, shifting is explored to its maximum. So every load used here, represented by a particle, is shifted to its maximum. This means until it collides with the next one. Now let us define this P and D as being the aggregate, P being the aggregate output of the population in time K, in this case normalized, and D as being the load demand of use N. So being this Dn 0 or 1, depending on whether a certain cell is occupied by a load use, then P, the aggregate output, must be a summation for each time period K of every load use D. So in the particle hopping model, the empty positions ahead of any occupied position can be used to regulate the population's aggregate output. This process is then implemented through this algorithm. This algorithm basically reflects the process I've just mentioned. It evaluates with this condition if the aggregate output P is greater than the target P star. And if it is, it means that some particles will have to be shifted ahead. Note that in this condition, we make sure that only the particles available are going to be shifted ahead. And then the output for a triangle waveform as the target is illustrated in this figure as an example. So in this figure, we are showing on the top the evolution in time of the normalized aggregate output that results from individual load responses, and below the positions of the responsive shifting actions in the two-dimensional lattice of cells. Hopefully, this animation helps in understanding this algorithm. And for this case, the target output was again a triangular waveform. And we see that the original randomly distributed load density starts to assume the shape here of a triangle waveform, as the load uses above, represented in this lattice, start to be shifted ahead, as you can hopefully see here. So what it happens that, as the title of the paper suggested, we intend to study load shifting as enabled by indirect control. Until now, we were only speaking about direct control. Possibility to incentivize users to postpone their consumption would be to actually broadcast the price incentives to be paid to users, this pi star, for every time there is a response to a shifting call. In this case, let us suppose each user bids a price pi n here to be rewarded for shifting load use n. So if that user receives a price which is higher than the price he has bid, is going to shift its load use. And in this case, to turn the CI algorithm to the one that simulates indirect control, it is enough to replace this condition that P is greater than P star, so the aggregate output is greater than the target, with a new condition that the price given is below the price that a certain user has bid. Then, by looking at these two figures, we take the first important conclusion from the study. And this is that by turning the control into an indirect control, the population size assumes a greater role. Because as we can see here, load following mismatches start to be evident. In this case, it was necessary to increase the population size from 100 to 5,000 to see an accurate output. Moreover, please note here that it is clear that the relationship between the aggregate load here on the top and the number of responses is not even linear. So let me introduce this new concept of velocity as being the number of shifting responses per time period. So it is formally defined as the summation of this Vn, where Vn is defined to be unitary if a particle n is shifted ahead in time k, and 0 otherwise. So it is important to note that with this new concept, we define the changes here in aggregate load necessary to yield P star, the target output, given by the difference in time of velocity. So then we start here from a linear bidding function as an example to plot a price velocity characteristic. This leads to the interesting fact that it exhibits hysteresis. This is caused by the supply dynamics introduced by the shifting process. This means that not only this characteristic doesn't follow the bidding function here, as some of the users that bid the price low enough are not actually available, but also it is not a sign increasing in velocity here as it is decreasing it. So, but for large density values, and densities here defined as the original lattice particle density, this process can be approximated by this ordinary difference equation This equation can then be used also to generalize the learning process to other densities and also to other target functions different from the triangular waveform. And by looking at this equation, we clearly see that the process is divided into two parts, one for increasing velocity and other for decreasing velocity. So this figure here on the right shows again the price velocity characteristic of the same experience as before, but this time by running a simulation with the equation I've just shown for different density values. And so by looking at this figure, it is clear that the equation is of course an approximation, but can nonetheless be a good one for large density values, which corresponds to this larger curve, so to speak. Note here again that the decreasing part of the characteristic is especially difficult to model. It is more evident here on the lower density curve when compared to the one by the simulation on the particle hopping model, so the first model described here. So this equation is the same as before, but this time manipulated to highlight the fact that predictability cannot be used without information on population velocity, which corresponds velocity again to the number of particles in the movement. So it makes clear that the relationship between the aggregate output changes, delta P star, the price pi star, depends on this new state variable, which is velocity. And so machine learning techniques could be used to help with utilities or other sending entities to predict individual class responses. However, a machine learning technique that could be used would have to be in agreement with this model. It has to consider always velocity data as an input. And throughout this study, we use always linear billing functions as an example, and we also didn't disguise any different type of market products. And so here is a set of different marginal billing functions that represent quadratic billings. This would be more realistic and would lead here on the right to this simulation that represents of course, a different characteristic from before. And this shows that the equation can be used to model different bidding functions as well. So to conclude, we've seen that load following accuracy depends on the load use density and population size when under direct control, which is something different from direct control. We introduced this concept of velocity as being a new state variable and representing the number of shifting responses in time. And this new concept has the role in price formation, emphasizing that the response output, this means the aggregate load, cannot be predicted without keeping track of velocity. This is no matter how large the population of users might be. So once again, the existence of these stresses we've seen in the characteristic provides evidence that elasticity alone is not sufficient to model the aggregate output or the aggregate response. So velocity is needed. So that is all. Thank you for listening, and hopefully I'm here to answer all of your questions.
Great, thank you. Are there any questions? There's nothing in the Q&A box yet. Oh, there's one from Mads, thanks. Do you see it?
Yeah, see.
Do you see it?
Okay, so let me read it. Thank you for the presentation. So I think there are 3 questions. Okay, so the first one, who decides the price curve for the HVAC? Individual or aggregator? Maybe I can answer to this first question. And so who decides the price curve actually is not really a relevant the decision maker here. So it can be the individual or the aggregator. So here we assume that it is always the individual, but we are not actually considering aggregators here, but if we do, the conclusions would be exactly the same. It's just a question of doing it for more than one individual. And so the second question is if can the price be considered a priority? Okay, I'm not sure if I understand the question, but I think so. I can explain the decision of the coordinator, for example, here. And so, as I've said, every user, or as you said, every aggregator, we assume is going to be a price. And then the control is made by choosing the lowest possible prices we can have for the number of load users we need to be shifted. And so the last question is, this work is similar to ongoing work on packetized energy management. So I think it's not really a question. Thank you for mentioning.
Yeah, I
would be interested to learn more. Thank you.
Yeah, so I permitted Mads to talk. If you want to add something, Mads, you can unmute yourself.
Can you hear me?
Yeah.
Yeah, sure.
Thank you for the presentation. No, so specifically on if the devices are basically just prioritized by a price, desired price signal, as you broadcast out the aggregate price, they're basically just sorting themselves automatically based on their own curve, right?
I mean, I think we are assuming here that someone, or I think we can call him the coordinator, would look at the prices that are broadcasted or bidded by the aggregators or the individuals. It would be the same, and that person would be in charge of making the decision based on the price. I don't know if I'm making myself clear.
Okay. No, I would just, it is very, I guess the approach is, I'd like the approach. The price curves, I think, will just be very difficult for any individual human to think about because it's just one device. And the other thing,
I think you're right.
And the other thing is, there are a couple related works around fitness where devices compute their own local fitness and sends that fitness number up to a coordinator. And then the coordinator sorts those fitnesses or updates their fitness table. There's some work out of Pacific Northwest National Lab on this. And then packetized energy also is a form of this, where the devices compute a fitness value and then make a request for the coordinator. And so some of the plots you showed are just very similar. And the cellular automaton that you presented is also very similar to some of the early work on packetized energy management. So you should take a look, and I'm happy to, offline answer questions or have a discussion about the topic.
Yeah, thank you very much. Thank you very much for mentioning.
Mm-hmm. Thanks for unmuting me.
Definitely be interested.
Great, thank you.